Hello and welcome back, and also a fresh welcome to many of you who have just joined our channel. With this video, we go back on track that we were on, and which was giving more and more examples of metric spaces and their properties. So we basically started this series of videos where we give more concrete examples of different metric spaces and talk about trying to give the impression of how versatile they are in all areas of mathematics. And we met this graph before. It's the graph of a tree. So this will be a regular tree where each vertex will have k children. And in this case that I have drawn it, k equals to 3. And then this continues forever. This example with k equal 2 triggered us to talk a little bit about cardinalities. I found those questions kind of interesting, showing that the set of ends of this tree has to be an uncountable set, basically just repeating the counter diagonal argument with zeros, ones becoming left, rights. And you could check those videos out, of course, but let's go back to metric world. So we want to equip this space with a distance function, and then let's see what will happen. The motivation for this example, the way I learned about this example, comes from this paper by Pekka Koskela, Con Gwen, and Juan Guang from 2019. And the short abstract is saying we give characterizations for the existence of traces for first order sublist spaces defined on regular trees. So regular trees here just mean every vertex having k successors. I won't get into the details of what sublist functions even mean in this context, but we will at least construct the basic setting of the paper, which is what is this space we're talking about, what is the metric, what is the distance function on it, and also we will talk about the measure on this space, because you need both a metric and a measure to even begin to talk about sublist functions on a space. So without further ado, let's go back to this and see if we can talk about the distance function. So first we begin by saying that each and every edge that you see here is an isometric copy of, because here only we care about distances, so we don't want to talk about ordering or algebraic properties of real line, but just the distance of the line segment 0, 1. So even though of course I couldn't fit this into the picture, we're assuming that this and this and this, all of them are just copies of 0, 1 with that much length. In particular, the distance of 2 points here is just how you would measure them, as if this was really the segment 0 to 1. So we begin with this, and then we can talk about the notion of, say, absolute value of x, and that by definition will be the distance. Okay, so that is just the distance for how distance works within one edge, but also the distance between two vertices equals the minimum number of edges needed to connect them. And this is a at least one collection of edges exists, just going back to the root and descending back to the other. So if you want to measure distance of this to this edge, there's always a collection of edges that does that. So the quickest way you can do it is giving you the distance between the two blues. So here you really have to actually go back to the root and then come back this way. So distance of the two blues here will be 4. Whereas if I have this one here and say this one here, the distance will be 1, 2, 3 between these two. So putting this data together, you can now talk about the distance of any pair of points, whether they are on the edges or the vertices. And by definition, we set absolute value of x for any x in this space to be the distance of x to the root. So this blue has distance 2 to the O, and this one also has distance 2. If you are at some point like this, then this will be about 1 point something, because there is one edge which is length 1, and then whatever is from here to complete it. So this is a well-defined notion. Boundary of x. So can we talk about boundary of this metric space? So this is something I vaguely talked about in the other video, just talking about cardinality of the collection of ends. So by the boundary of x, intuitively we talk about points like this who are waiting to be reached by an infinite collection of edges. But we can precisely actually say that the boundary of x is identified with the collection of all infinite geodesics starting at the root. So by an infinite geodesic, we mean an isometric copy of half line, which is this as a subset of R of 1 is with the usual distance, and if we have an isometric copy of this inside your space X starting at 0, then this is again basically giving you an infinite collection of edges. So you want to move isometrically to the half line starting at 0. Say you go this way. Because you want to be isometric, there's never a talk of returning. Therefore, you have to keep going all the time. So you go down this edge. Again, there's no coming back. You have to go that way. So there's never double covering anything. So the property of isometry forces you to just keep going. And because this process also doesn't have to stop, you can always continue. Therefore, you get a copy of 0 plus infinity inside your space X. And any such isometric copy is just a point in the boundary. So a point in the boundary is nothing other than a geodesic, an infinite geodesic starting at 0. Okay, that's an important notion in the paper that I just showed you. Actually, the whole point of paper is about talking about limits of functions as you approach the boundary of this space. Okay. To talk about sublove functions on this space, something is not quite right, and that is the huge size, huge diameter of this space. In going down, you quickly move up by integers, and then of course the distance from the root to any boundary point will be infinite, obviously. And if you talk about measure, you can talk about Lebesgue measure basically on each edge, and then that also becomes a huge measure. So to kind of make this space manageable and tamer, what we can do, and what is done in this paper, is to apply weights. So the simple idea of weighing down this distance maybe can be first explained in, if I talk about just R1. Okay, so you have the distance of any 2 points x and y. The original Euclidean distance is just absolute value of x minus y. But then also you can suppose there is some lambda, which is a non-negative function from R to R, and say it's nice, for example, continuous, and you can integrate and whatnot. Then you can also introduce a new distance between x and y, and that will be, okay, if you integrate it from x to y, the function 1, that would just be absolute value of x minus y. So this would just be the original distance. So therefore, the idea of weight is just to weigh it down by this function lambda t. And if this lambda t is, say, less than 1, then this gives a shorter distance than the original one. And if this lambda is, say, integrable over whole R1, we could actually have that the whole diameter of the real line with this distance be finite, because, well, what is the longest distance you can get? That will be basically distance to infinity, and that will be, say, from x to all the way up to infinity, lambda t dt, and that can be finite, of course, by forcing lambda to go down pretty fast. So that's the idea of how you can play around with starting with some distance, and then, so this is basically the length element, the element with respect to which you integrate in this Euclidean norm. So you start with that, but then adding this weight, you construct a new metric that probably is smaller values, and you can obtain different things. And what happens in this paper, they do a similar construction on this tree. And the reason it's so easy to do is basically by using this distance from the root, you reduce the question basically to a one-dimensional thing. So this is a radially invariant, say radially symmetric object. So that means if you are here or here or here, basically a sphere around the root, absolute value of x doesn't change. So you start by a function that is also radially symmetric. So you start with some, and because here you start at 0 and you always move forward, you only need a function. All the analysis is only in the half line. So you start with a function defined on this half line that is non-negative, and also you can integrate. So locally integrable. Of course, this is with respect to the Lebesgue measure on R of 1. Then you define the distance between the new distance So the new distance function on your metric space X will be as follows. So if you give me Y and Z on this tree, there is this unique geodesic, unique path that connects Z to Y or Y to Z, doesn't matter. And then you have this element, length element, which is, when you localize, it's just the Lebesgue one measure. And then, of course, you use this weight coming from lambda. Of course, you cannot put lambda x. Lambda is a real valued function on real line, so you put absolute value of x. So let me show you in picture what is going on here. So you have this, you have, say, this, and then you have further subdivision. So suppose your y is here, and your z is here. So suppose z is here and y is here. So the unique geodesic, so there is always a geodesic, and it's in previous distance. Of course, here we are yet to construct the d distance between them, and that was, okay, you travel the shortest number of edges needed to connect them. Of course, you can imagine that this is already happening within deeper levels of the tree, but that doesn't matter. So if you integrated the function 1 here, this would just give back the same previous distance, because integrating this is only just how far you are from the root, and locally it just means the Lebesgue measure. The previous distance, which was isometric to 0, 1. But now, if you are somewhere along this path at x, from here to here, for example, this segment, if it originally would be, say, 0.3 centimeters, in the version of the distance where the whole edge is a copy of 0, 1, but now this will be comparable to absolute value of x, lambda evaluated at absolute value of x, times this. And depending on this lambda, this can be much shorter. So the local integrability makes sure that you actually get a finite value for these. And if you require much more from lambda, for example, integrability over the whole thing, that would mean that even if you compare this root to something on the boundary going down this way, so the distance of 0 to something on the boundary would even be finite if lambda is integrable, because in that case this would be just integrate from 0 to infinity all of lambda t dt, and that would be finite if this integral is assumed to be finite. So by choosing the right lambda, we can even make this whole metric space with finite diameter in the new distance d. So the new distance d can turn this tree into a bounded metric space where the distance of any pair of 2 points is bounded from the above by the same constant. If you give two different points on the boundary, the reason I know that their distance is finite is the worst is to go back to the root and then come back with this, so it will be twice as much as this quantity. So that's how you can improve metrics, and that is a common thing in metric analysis to replace original distance functions with the ones that are more suitable for our needs. So because our focus is always on distances, I won't give too much detail of the way you construct the measure, but it's basically very similar, because actually in one dimension measure, so you can regard this quantity which we saw above as the length element, but also you can regard it as the measure element, so as a measure, because Lebesgue measure L1 in real line is comparable just to the area element, the length element. That's something unique about just one dimension. So to construct a measure on this space, now equipped with this distance, we similarly start with some function mu, which goes again from half line into R, and it's non-negative, and it's again locally integrable with it, of course, as a real valued function. Then here is some abuse of notation. I want to use mu also for the measure that will be constructed using this function. And one notation to show a measure is saying that this measure d mu or mu comes from a measure the absolute value of x by integrating it against a weight, and here you can guess that the weight is this function. So this is a function which is used as a weight to integrate against this measure to get a new measure. So one measure is a function times another measure, and that's a common thing in any measure theory course. And so this really should be that we define it this way. So we have this function, we use it as a weight against this measure to construct our new measure. And if you are not familiar with this notation, let me draw a quick picture of how it works. So if you have to give a measure, because, well, measure is countably additive, so you only need to consider sets like this, which lie only in one edge. So suppose it lies in one edge here. Then I have to just give you the measure of such an E. And what this notation means, it's nothing other than its meaning that this is integrate over E against this original measure, which is again just Lebesgue L1 when you just reduce to this one edge. And but if you integrate this itself, that will be just the Lebesgue measure of E. You integrate instead the function mu of absolute value of x. And now you can see that if you have a similar copy of E here, exact same copy, in Lebesgue measure they would have the same value. But now, because you're integrating different quantities here versus here, exact same set here could have a measure very different from the one up here. And for similar reasons to what happened with the distance function, you could have, depending on how nice this mu function is, you could have that the measure of the whole space X is actually finite. So this is a possibility. So let's go back to this paper. What I've done is just to show you the basic construction of x together with the distance d and the measure mu. And you can see that they also assume additionally the second line from below that lambda to power p divided by mu which is now a function again defined on the half-line a real valued function. You want some integrability for that. These are all for further technical reasons. Then xd mu is a metric measure space. These are very, very important objects in analysis of metric spaces. So these are spaces that have a metric and a measure, usually with some compatibility between them. And on them, you can define Sobolev functions, which of course cannot use any notion of partial differentiation or anything. So these are Sobolev functions constructed based on upper gradient approach, and then the rest of the story. So what they prove in this paper is by assuming some boundedness of some quantity, here that would be this Rp, so it's some power of lambda, some power of mu, and k is the number of, it's k3, so k is just one number. And the theorems look like this. So if you have this boundedness for Rp and also boundedness of a measure, then every Sobolev function has a well-defined boundary values. So we can talk about what are the limits of the functions as you approach the boundary of the set, in this sense up here. So they were interested in the question of whether to any Sobolev function, whatever it is, however it is defined on the space, that issue put aside, when do we have limits for every Sobolev function defined on this as you approach the boundary? Yes, again, my goal isn't to present to you this paper in detail, but I believe that this was a very nice example of interesting things you can do with apparently simple objects. And also we learned the trick of how to weigh down a distance to construct a new distance function. Of course, all of these are left as exercises that prove indeed that this d does define a metric, which means check the triangle inequality, and that I'm not going to do for you. So this brings us to the end of this video. We will be talking more about more concrete metric spaces. Until then, stay well.